Alright, welcome to the review for the Calculus Fall Final Exam. So if we look at question number 1, it says find the limit as x goes to infinity of the given function. So if we remember from class, what we want to do is think about like horizontal asymptotes. So we can either do it that way and picture what these graphs look like by finding the horizontal asymptotes where we had the three rules. So starting with, we look at the highest power, which is cubed and cubed, and because the powers are the same, we just divide the lead coefficients, which would be -4/5, so our answer is C. If you forget those rules, though, what we can do to also get that it's C is we can take each term in both the numerator and the denominator, and divide each term by that highest power. So we end up with the limit as x goes to infinity of 3x over x cubed minus 4x cubed over x cubed all over 5x cubed over x cubed minus 7x over x cubed plus 8 over x cubed. And when we simplify that a little bit, the limit is 8 as x goes to 0, we get 3 over x squared minus 4 over 5 minus 7 over x squared plus 8 over x cubed. And what that does for us is now we have our powers in the denominator, and as we evaluate this with x going to infinity, 3 over some really large number goes to 0. On the bottom, -7 over some really large number when I plug in infinity goes to 0, and 8 over some really large number goes to 0. So I'm left with the limit as x goes to infinity of -4/5 because everything else went to 0, and the limit of a constant is the constant, in this case -4/5. Number 2, we're given the function f of x equals x cubed minus 12x. Which statement about this function is false? Before I even do it, I'm going to look at the problem, and I see we're looking, does it have one inflection point? Is it concave up? Does it have two relative extrema? Is it increasing? Does it have a relative minimum? So when I see those words, I know that I'm going to have to take both the first and second derivative of the function. So I'm going to go ahead and find the critical values by taking the first derivative. So f prime of x is going to be equal to 3x squared minus 12. I'm going to set that equal to 0 to find my critical values. And let's see, when I add the 12 and divide by 3, I get 4 equals x squared. So plus or minus 2 is equal to x. So I have critical values at -2 and +2. So the function has two relative extrema. That is true, and we're looking for a false statement, so C is out. We don't know yet if it's increasing between -2 and 2, but we've got some other things to check. So I'm going to also find the second derivative, which is just going to be 6x. I set that equal to 0, and I get an inflection point at x equals 0. So that's an inflection point. And so the function has one inflection point. That's also true. So A's out. I don't know if it's concave upward or not. And I still don't know if it's increasing or if it has a relative minimum at 2. But what I can do now is make my chart. And I'm going to go ahead and use the second derivative test. Because the second derivative test said that if I take any of those points, I can evaluate them into the second derivative. So I take the -2, plug it into 6 times x, that's a -12, so that's a negative value. Plug in a 0, I get 0, that doesn't tell me anything. And if I plug in a +2, I get a positive value. Well, what this tells me is that right here, I've got a max at -2, I've got a min at +2, and if I have a maximum value at -2, that means my function has to be increasing up until -2, because that's my maximum value. Then it starts to decrease. So if we're looking at this, does the function have a relative minimum at +2? Yep, it does. That is out. The function is concave upward for x is greater than 0. Well, concave upward, remember we're checking what is the sign. So concave upward for x is greater than 0. That appears to be true because we have a positive second derivative when x is greater than 0 right here. So that's also true. So that means we're left with the function is increasing for values between -2 and 2. Now it's got to be decreasing because between -2 and +2 we go from a max to a min. So our graph had to look something like, if that's -2 and this is +2, you'd have a maximum value here, minimum value here. So our function had to be decreasing in between those two. So our answer is D. Number 3. Given that function, it has a local maximum at, well, again, I need to find the critical values. So I'm going to start by taking the first derivative, which is 3x squared minus 12x plus 9. Set that equal to 0. And then we're going to go ahead and solve this. I'm going to pull out a 3, so I've got x squared minus 4x plus 3. That looks like it's factorable to be x minus 3, x minus 1. So I'm left with x equals 3 or 1 as my critical values. So 1 and 3. And since we're finding a max, I could use the first derivative test right now. Or I'm going to go ahead and take the second derivative. And I get 6x minus 12. And once again, I can apply my second derivative test. I'm going to check the values at 1 and the value at 3. So at 1, when I plug 1 in for x, I have 6 times 1, which is 6, minus 12, which is negative. And at 3, I get 18 minus 12, which is 6, which is positive. So once again, negative second derivative means I have a max. A positive second derivative means I have a min. I'm looking for a local maximum. So the max is going to be at 1. Number 4, find the limit as x approaches 5 of 2x squared minus 4x plus 7. Remember when we did this way back in chapter 1? First thing we want to do is just see if we can evaluate it. Can I evaluate this function at 5? Meaning, can I plug in a 5 and have it be defined? And in this case, yes, because it's just a polynomial. So to find the limit at 5, I'm just going to take my function and I'm going to plug in 5. So I have 50 minus, not 40, 20, plus 7, that's 30, plus 7 is 37. Number 5, same thing. It's the limit as x approaches 2 this time of that function. I want to first check, can I evaluate the function at 2? That answer is no, because our function is not defined at 2. So I have to use one of my other rules. The rules we had were factor. We had conjugate, multiply by the conjugate, and we could sometimes square. So we had a couple different rules that we could use. We are going to try to factor this. So the numerator can factor to be x minus 2 times x plus 3, and the denominator is just x minus 2. And now that I do that, now I can cancel out those x minus 2's. So I have the limit as x approaches 2 of x plus 3. Now that is a function that I can evaluate at 2. So if I plug that in, 2 plus 3 is 5. Number 6, minimize the sum of a number and its square. So how do we minimize a function? Well, to minimize a function, we have to have a function, and then we need to find its derivative, set it equal to 0. Basically, it's going to be one of those critical values. So we're minimizing this, the sum of a number and its square. So we're finding the sum So our function, f of x, is equal to the sum of two things. Well, what are the two things? It's some number and its square. Well, its square is that, x squared. So there's my function that I'm going to minimize. So I'm going to minimize that by taking its derivative, which is just 1 plus 2x. I'm going to set that derivative equal to 0. Subtract 1. So negative 1 half equals x. So that's going to be my value. I'm minimizing that. So that answer is A. I don't have to check anything because that is going to minimize. I don't have any other constraints in this problem. If it said like it has to be a positive integer, I would have to go from 0 to infinity as my values. And remember, if there are constraints, the minimum might come at one of the two constraints, or it might come at the critical value itself. 7, we are going to skip. This is a problem for when we come back from break. We have to do anti-differentiation to find this value, so we're not going to touch it right now. Number 8, at x equals 3, the function given by f of x equals x squared when x is less than 3, and 6x minus 9 when x is greater than or equal to 3 is one of these things. So first, let's picture what's going on here. So we have a function, a piecewise function, that is first defined as x squared. Well, x squared looks like that, a nice parabola. And this parabola stops when x is equal to 3. So there's an open hole right there. But we know that that ordered pair should be, because it's a parabola, should be 3 comma 9, because it's x squared. So all the way up until that point, it's defined. Okay. Then we switch to the other part of the piecewise, 6x minus 9. Well, that's a linear function that starts way down here at negative 9. And it's going to move this way. And I don't know exactly where it goes yet, but we can evaluate it. What happens at 3? Well, at 3, I get 6 times 3 minus 9, which is 18, minus 9, which is 9. So f of 3 is 9. Well, that happens to be the same point that I was already given, so now that circle gets filled in, and now I have a slope of 6. So my graph looks something like this. So it's a parabola all the way up until positive 3, and at 3 it becomes a line. Well, just by looking at this picture, is the function defined at 3? Yes, it is, because we see right here when x is greater than or equal to 3, we get an output. It's defined, that's out. B, is the function continuous but not differentiable? Well, it is continuous because that hole is filled in. So we'll come back to that one because it's a maybe. Is it differentiable but not continuous? Or for it to be differentiable, or for it to not be differentiable, there has to be a kink, a jump, or a vertical asymptote. Well, I don't see any of those things going on here, so it's definitely not that. And neither continuous nor differentiable. Well, we know for sure it's continuous, and then both continuous and differentiable. Well, so once again, so we're deciding between B and E. Here's what we need to remember. So is there a kink, a jump, or a vertical asymptote in this problem? No, there is not. So that means this function, f of x, is for sure differentiable. And we discussed in class that differentiable implies continuous at x equals a. So if the function is differentiable at a, then it's continuous at a. Because this function is differentiable at 3, we can find the derivative because there's no kink, jump, or vertical asymptote. then it's also continuous at a. So this function is both continuous and differentiable. Number 9, if 3 cosine of x plus the sine of y is equal to x squared, find dy over dx. Remember, this notation says take the derivative of the function with respect to the x variable. And I see a problem already because that is not an x, that's a y. So we're going to have to use our implicit differentiation to finish that. So we're going to start by taking the derivative of the entire function. So we've got 3 cosine of x plus the sine of y equals x squared. We're going to take the derivative of this whole thing. So the derivative of 3 cosine of x is negative 3 sine of x. The derivative of sine of y is cosine of y, but since we are taking the derivative with respect to x, we need to also multiply that by dy dx, and that's equal to 2x. And it says find dy dx, so we're going to have to get dy dx by itself. So we're going to add the 3 sine x to the other side, and then we're going to divide everything by the cosine of y to cancel that out. And so I'm left with dy over dx is equal to 2x plus 3 sine of x over cosine of y. And that appears to be answer B. Alright, number 10, let f be differentiable. That satisfies f1 is 7 and f4 is 3. Which of the following conditions would guarantee that the tangent line at C is parallel to the secant line joining 1 f of 1 and 4 f of 4? Well, if we read this, so we have some function. I'm going to draw some function. Okay, we have f of 1. So this point right here is 1. And then we've got some other point over here that is 4. Says, so if we have a secant line from 1 to 4, which of the following conditions would guarantee that the tangent line at C is parallel to the secant line joining? So we have a tangent line somewhere in here that is parallel to that secant line, something like that. So maybe right there, that's point C. Well, that to me looks like the mean value theorem. So the mean value theorem says that the slope of the secant line is equal to the slope of the tangent line at a point somewhere between the intervals. So all we need to do is figure out what is the slope between 1 and 4, what is the slope of the secant between 1 and 4, and we've got all the information we need. The slope of the secant is equal to 3 take away 7 over 4 take away 1. I just did y2 minus y1 over x2 minus x1. I get negative 4 over 3. So the slope of my secant is negative 4/3. So that means that to guarantee that there's some c in between, because it's differentiable, I need my derivative at c to be equal to negative 4/3. That's just an application of the mean value theorem. 11. H of x equals 2 cosine of x over 2. Find the second derivative with respect to x. So this is going to start by taking the first derivative. So we're going to have to apply the chain rule. So it's going to start, so dy dx equals negative 2 sine of x over 2, that's the derivative of the outside, times the derivative of the inside, that x over 2 is just 1/2. Well, those cancel out, and I'm left with negative sine of x over 2. That's my first derivative. My second derivative now is going to be the derivative of this function, which the derivative of sine, of negative sine is now negative cosine x over 2. Again, we do the chain rule, so I multiply that by 1/2. And my second derivative is now negative 1/2 cosine x over 2, which is E. 12. Find the function whose derivative is 6x minus 8 and whose graph passes through the point 2, 6. Again, we're going to skip this one. What we could kind of figure it out, because if the derivative is 6x minus 8, we know that the function had to at least be 3x squared minus 8x to get that derivative. But we don't know how to get that plus 10. Again, this is an anti-differentiation problem. You could, at this point, we know it's either down to C or D, and we could just plug in the 0.26, see what happens, which one gives us 6 when we plug in 2. So if I plug in 2, I get 3 times 4, which is 12, minus 16. 12 minus 16 is negative 4. Negative 4 plus 10 is 6. So it would have to be D. 13. The graph of f of x is 5 over 2 minus x. It's concave downward for all x such that one of these has to be true. So concave downward, that's going to be the second derivative of f. So we're going to start by finding the first derivative. We are going to do, you could do the quotient rule, but what I would rather do is rewrite this as 5 times 2 minus x to the negative first power. Just bring that entire denominator up, make it a negative. So now I have negative 5 times 2 minus x to the negative second, chain rule, times negative 1. So my first derivative is 5 times 2 minus x to the negative second power. And then my second derivative is going to be negative 10 times 2 minus x to the negative third. And then once again, chain rule times negative 1. So I get 10 times 2 minus x to the negative third, which can be written as 10 over 2 minus x to the positive third. So there's my second derivative. I need to find the inflection points. So where is it going to be concave? Down. So 0 is equal to 10 over 2 minus x cubed. If I multiply by the denominator to the other side, I get 0, which doesn't do me any good. So remember, concavity with points of inflection as well as critical values for the first derivative. We are checking where is that derivative equal to 0, either the first or the second derivative, where is it equal to 0, and also where is the function not defined. Well, this function is not defined when x is 2. So we have one value that we need to worry about, which is what happens at 2. So I'm going to check both sides of 2 into my second derivative here. So I'm going to check 1 and I'm going to check 3. If I check 1, 2 take away 1 is 1. 10 over 1 cubed is positive. And if I check 3, 2 take away 3 is negative 1. Negative 1 cubed is still negative 1. 10 over negative 1 is negative. So we have concavity, we have concave upward when x is less than 2, and concave downward when x is greater than 2. So that's going to be answer E. 14. Find the linearization of that function at x equals 2, which means write the equation of the tangent line for the function at x equals 2. So we know from experience that if we want the equation, we're going to have to have a point. So it's going to be the point at 2, comma, so it's going to be 3 times 16 minus 5 times 8. 48 minus 40, that's going to be the point 28 is what is the point that I'm dealing with. So we're going to start by first derivative, 12x cubed minus 15x squared. I'm going to evaluate that at 2. So 12 times 8 minus 15 times 4. 96 minus 60, which is 36. So my slope is 36. So A is out, B is out. It's either C, D, or E. And now I can use my point slope form or slope intercept form, whichever one you choose to use. Y minus 8 is equal to 36 times x minus 2. So y is going to be equal to 36x minus 72 plus the 8. It's going to move it to the other side. 72 plus 8 is negative 64, which is answer E. And finally, the last problem on day 1. H of x is equal to radical 2x. Find h prime of 2. So h prime of x, we know by now that if I have the square root of x, I'm taking the derivative of that function, it's equal to 1 over 2 square root of x. We're just going to have to apply the chain rule. This is going to be 1 over 2 radical 2x times the derivative of 2x, which is just 2. Those 2's are going to cancel out, and I am left with 1 over radical 2x. There's my function. I'm going to evaluate h prime of 2, which is 1 over radical 2 times 2, which is 1 over rad 4, which is 1 over 2, which is answer B. That's going to do it for day 1 review for the final exam, and day 2 will be posted shortly.